Good afternoon, everyone. Just going to give it a couple seconds, let everyone get filtered in here, and then we'll get started for today. Alrighty, I see that number jumping up really quick, so let's get started. Good afternoon, everyone, and thank you for joining us today for the live webinar, Managing the Hazards of Burnt Wood Dust Processing. Before we get started, just want to extend a big thank you to VETS for sponsoring this webinar today. I'm Alex Retsky, Digital Media Project Specialist for Annex Business Media, and I will be one of your moderators for this session. Before I pass it over to your speakers this morning, I'd like to take a moment to just go over a few housekeeping items. Firstly, this webinar is being recorded, so if for any reason you have to leave early or you miss part of the presentation, a link to the recording will be emailed to all registrants within 24 hours. Secondly, the audience is in listen-only mode, so cameras and microphones will be turned off for you. However, the chat and Q&A function are open to you, and any questions you may have can and should be submitted into the Q&A tab at the bottom of your screen, and we will answer all those questions at the end of today's session. Now I'd like to introduce First, we have Mark Oler, who will be assisting me in moderating. I'd like to introduce Francis Petit. Francis has over a decade of experience specializing in industrial ventilation and dust collection systems. He brings an NFPA performance-based approach to complex explosion protection systems in a range of industries. For example, mining, wood fiber, agriculture, and biomass, and is VET's point of contact for dust hazard assessments throughout Western Canada. I'd like to pass it over to Mark and Francis for their presentation.
Good morning, everyone, and thanks for joining in. Here, Francis Petit. I guess I'm French speaking, so forgive me if I'm making a couple little typo in English there, but I'll try to do my best to represent the language English there. And I guess we have Mark as well with us, and I'll let Mark introduce himself.
Oh, thank you. My name is Mark Oler, professional engineer in Alberta in BC. I work with Francis as a project engineer at VETS, and my favorite way to describe this is I handle complex engineering tasks and project management.
Fantastic. Thanks, Mark, for that. Well, I know we only have about an hour, and I'll try to get everybody out in less than an hour. So we do have a complex task, which is, learning about burnt wood and the hazard of burnt wood. And so let's get started. I'll just skim over this briefly. Alex did a great job already at presenting who I am. So I'm a professional engineer, and I'm also director of engineering at VETS here. And I've got about 15 years of experience, and I'm recently a tortoise person. My kids both have a tortoise as of like a month ago, so I'm learning a lot about tortoise. I guess tortoise are a ground animal as opposed to turtle actually a water animal. So I've learned that actually. My kids taught me that, so that's pretty cool. All right, so we'll go over the presentation summary. So just briefly skim over who is VETS Sheet Metal. We're going to look at forest fire stats, dust properties, and we'll look also at the abrasive challenges, the contaminant and containment and dust extraction. We'll also skim over dust abatement using water technology. And there's a pretty interesting case study we'll look at the end, and we'll wrap it up with awareness solution and question and answer. So who is VETS? We have often heard the people calling us to fix their animals, but it's not, we're not in the animal industry. I guess we are a sheet metal company based out of Edmonton, Alberta. We do have also an office in Burnaby. And it's a pretty cool history. So it was founded in 1921 by veterans Fred Rayner, and therefore like the name VETS for he basically hired a bunch of different veterans World War One and founded the company there. So we kind of kept the name that goes kind of with the idea how it was founded. And to this day, also we're supporting the veterans communities around Western Canada, and it's a fourth generation. So the current owner of VETS is Sean Rayner. And we do have an ESOP program for those who don't know. So it's an employee shared ownership program. So we have about 30 people in our company that owns shares of the company. And we do offer, like our main, I guess, focus is Western Canada, but we do offer engineering throughout Canada as well for some support. All right, forest fire stats. That slide, actually, I've learned some interesting fact from Canada. So if we focus on stats just for Canada for forest fire, so I pulled the source from Canada National Fire Database, and on average, there's about 8,000 fire occurring each year. So think about it. We only have 365 days a year. And so that's a lot of fire every day in Canada. It's quite impressive. And the area covered by forest fire, this is again an average, but it's 2.5 million hectares. For those who don't know what an hectare is, think about it as about 2 times the size of Prince Edward Island burnt every year. So that's a lot of forest being devastated by fire. And the salvage logging and forest fires are typically between 12 and 15% of the burnt number. So we can harvest, in that range of percentage to, recoup some of those logs to get processed in the industry. So dust properties, when we talk about dust properties, can kind of see a little bit the raising challenge. There's so many different species throughout Canada alone. So we look at British Columbia, there's, Douglas fir, western red cedar, hemlock, lodgepole pine. These are kind of the main species, but there's obviously other ones. In Alberta, we have the spruce, pine, fir. Ontario, it's a mix of hardwood, so maple, birch, and softwood by spruce and balsamic fir. In Atlantic provinces, we'll have balsamic fir, white spruce, hardwood like birch and maple. For this specific presentation, though, I mean, we can brought it a little wider, but we felt that it was important to focus a little bit on a certain species, which is softwood. And obviously hardwood are another topic in itself, but softwood would be addressed in this presentation. So just to start with a pool, let's see maybe if you guys can test your skills. So we have a question here. So what is the leading wood species harvests in Canada for the dimension lumber industry? So we have a different option on the screen here. I'll let a few moment for everybody to write their answer. So the Douglas fir, we have larch. Option B would be hem fir and aspen. C would be spruce, pine, and fir. And D, palm tree, olive tree, and lemon tree. Sounds interesting, that one. Let's see who's gonna answer what. We'll give call it another 30 seconds. And by the way, I cannot vote, so I can't change the results. Sorry, guys. I've just seen that host and panelists cannot vote, so I'm a bit disappointed, but it's okay. All right, so we've got 6% for A, we got 4% for B, we got 89% for C, and a little disappointed, only 1% for D, but hey, it's okay. I'd love to be in California or somewhere where we can officially say that it's a possibility. And I guess the Mass did also win I guess the selection. So it is, yes, spruce pine for that is the highest or the most predominant species harvest and process in the dimension lumber industry. So congrats to everybody. We'll have participation point for everybody on that one. Okay, moving on to the next slide. There we go. I had a little bit of a spin to present the results there for those who didn't get it. Okay, so dust properties. For those who don't know, I guess, how dust gets tested when it comes to explosibility, I'll spend a few moments to explain the detail around this. So there's different lab testing we can do. The most common one would be a characterization of ASTM E1226. And in there, it's quite well documented, and it shows how to prepare the sample in the lab and then test it in the chamber two that you see on the I guess where my mouse is hovering here. So this chamber is normally a 20-liter chamber. So there's two sides that you can get 1 cubic meter, which is much larger. But the 20 liters kind of the common in most labs where they have it. The 1 cubic can be tested in certain circumstances, but the most popular is definitely a 20-liter. So they are typically preparing the sample to the E1226. So the preparation of the samples normally come with a certain percentage of, or certain mass of a sample. Typically, like depending on each lab is a little bit different, but they are requiring half a kilogram. And they will dry the sample to about the 3% or a bit lower possibly. And they will also prepare it by grinding the sample to a particle size to 75 micron and below. That's kind of the target. So there's two options when you prepare a sample. You can also do a test, they call it as is. So they will take the larger particulate and they'll remove it by sieving. So they'll sieve through about a 480 micron siever, and it'll keep everything that passed through the sieve, which is a finer particulate, and they'll test that dust. So there's different, I guess, in the industry, different ways of seeing the as-is result and the grinded results. I won't go too much in details, but for a bag house per se, a dust collection that has a bag, there's a lot of fine particulate that will build up on the bags that could be extremely fine. So the grinding is very important to grind it to the 75 micron envelope to make sure that you have a representative of like kind of the worst case scenario, because dust particulate will actually affect the results. And so if we look at the characteristic on this chart here, there's something called KST, which is the rate of explosion pressure rise. What it means, in other words, is if you take, for instance, gravity. So you throw something up in the air, it's going to fall back down a certain, basically a certain acceleration. It's the same idea with the KST. It's a pressure acceleration. So how fast the pressure will build up in the enclosure. And it's measured in bar meters per second. And Pmax would be the maximum pressure that same dust can generate in the enclosed environment. There are also some other useful information like minimum explosion concentration, the MEC, and it's typically in a dust cloud. So there's a dust cloud generated, and then we can measure the number of gram in that dust cloud in, let's say, 1 cubic meter. And so like the lab will do different tests at different concentration, and they'll notice when it start exploding. So not enough dust into a dust cloud will not necessarily create an explosion. So as the dust concentration gets more predominant, then you'll have an explosion. There's also something called the minimum ignition energy, the M in millijoule normally. So the smaller the number for that, the more exposed or the more easy it is for a spark or something with low energy to create an explosion. So if, let's say for wood, I've seen some 30 millijoule to 20 millijoule is kind of the for green wood. It's kind of the where it can be seen in. But some dust, like let's say epoxy fiberglass, can be like extremely low, like in the single digit. That means it's very dangerous. Any spark or any even static discharge could cause an explosion potentially. So the lower that number, the more challenging it is on site. And there's something called the MIT, and it's not a university. It's the minimum ignition temperature. It's not in Boston there. Sorry, that's a dad joke there, by the way. Okay, so to the right here, we have a practice for the proximate analysis of coal and coke. So ASTM D3172, and the reason why I bring this, you might be scratching your head saying why coal and coke doesn't really match with burnt wood. What happened is in the burnt wood, if you look at a tree when you harvest it, there's sap, there's oil, there's all kinds of tar, or even basically organic compound in the bark, trap come in between the bark and the tree itself. And so that could contribute for an explosion. So there's a test where in under a non-oxidization atmosphere, so like let's say nitrogen or something like that, they will heat up the sample. They will weigh before they put in that enclosure, and then let the heat kind of dry that sample without oxidizing anything. And they'll weigh after, and then they'll be able to characterize the percentage of the volatile organic. And so there's that contribution that could also explode during an explosion, I guess, for trees harvest. And that's important to characterize because sometimes it's 15-20% of that total weight of the sample. So it could be significant. All right, so let's moving on to the next one. Oops, I feel I didn't skip a slide here. So here's an example of a result that we've got, and that's kind of what triggered our concern, I guess, and kind of triggers the topic that we have today. And so we had this sample that we collected at one of our site and one of our clients, and so we did a test with greenwood. And when I say greenwood, it's a harvested tree that hasn't been processed, I guess, and burnt wood. And so the results were really interesting. So like to the top left here, you see the sample. So this is greenwood, the Barker sample as received here, while being sieved. And burnt wood, the Barker sample as received. So we see like it's more of a darker and the finer particulate. And we've tested in two different ways. Like I was explaining, there's the way that we can be tested with doing just a sieving, which shows like below 500 here, and for the debarker. And then there's one way to actually grind the particulate and or the dust, and then you get the 75 micron that you keep here. And if we look at the numbers, like the slide before, we learned that KST and MEC and MAE, so we'll be able to identify those values. So there's the Pmax. So for greenwood, 7.2 bar. Okay, I see, Mark, you have maybe a question here.
Oh, for sure.
Yeah.
I'm seeing that we want to know what's so dangerous about having a new dust that has a higher KST.
Yes, absolutely. So I'll definitely get to it right away, but I was keeping it for a little later, but let's do that right now. So higher KST, if you think about it, it's how violent and how fast you have to react for an explosion to have mitigation device or equipment in place to capture either the propagation of the explosion to isolate or to vent properly. So the faster, we're talking like, a KST of, let's say, 61 and 100 is still very fast. All right, no matter what, it's not like fire where you can you throw a match and a fire and you have minutes to escape. If it's in a building or whatever, like this happens in milliseconds, extremely fast. And so, but even in millisecond, every millisecond is important. So if it's even faster, one explosion as opposed to the other, the propagation of the explosion and the pressure, that will change also how what kind of equipment is used to isolate or to vent. So a faster reaction time of an explosion, which I'm referring right now to the KST, will also lead to a requirement as if you're using just an explosion venting. And venting, what it is you have a vessel, and the vessel is designed for a certain stress or capable to withstand a certain pressure, I should say. And so most vessels are designed to under a single digit for PSI. And we've seen like, the Pmax, a 7.2, I don't remember the conversion, but it's maybe 80 or 90 PSI. So if it can develop a full pressure in that vessel that's rated for, let's say, a 5 or 4 PSI, it will explode because it won't be able to hold that pressure. So the explosion vent, what it is it's a releasing system that will cause the pressure not be able to reach more than what the enclosure is rated for. And so having a fast explosion, fast acceleration means you need a larger opening or a weak point with the vent to be able to vent properly and release that pressure before it reaches the maximum pressure rated for that vessel. Mark, anything you want to add to this or?
No, that was a great explanation. Keep them coming.
All right, perfect. So looking at the values, we see that green wood is 61 KC and burnt wood 108. And even if we look at the values of just the sieve itself, 51 and 97. So there's consistency on that specific sample. And that's where I want to make sure, I guess, everybody understand. And I'm not saying by any stretch of imagination that burnt wood is always more explosive than green wood, because that would be completely a statement that's not proven by the industry yet. And when we got that result, I started doing some research and digging into certain other tests that were done. So we thank also like Jensen Johansson and sorry, I have a blank there, but Foskey helped out. The CRC also did help out. These are labs that are specialized in exposure dust testing. So appreciate everybody contributing. But what I found is in the industry, there's a little bit of a misunderstanding of burnt wood because there's not enough dust test for that specific part of the industry. And there's a challenge too. I want to spend a little bit of time on this slide because if you think about it, each species has its own marker when it comes to explosibility, and it is also influenced by the particle size. It's influenced by the species, even the region where the species has been harvested. It's influenced by, let's say, if it's a burnt wood, by how bad the fire was and how much oxygen during the combustion there was. There's a lot of different factors, so it's very difficult. Even if you harvest a tree and then you test the dust that's a tree that was burnt, you might not get the worst case scenario. So just be careful when you do a dust test and understand that the result you're getting is for the tree you're harvesting. It's not for a blanket test that can give you a good feeling of what to expect. So another pool that I'd like to ask here. So this is specific on the difference between burnt wood and charcoal wood. And so let's pull maybe the pool there and see who can answer properly. So like there's A, B, C, D, and this one is you can actually select multiple options if you think that's the answer there. But the first would be burnt wood is an open air and uncontrolled combustion. And then the B would be charcoal wood is a combustion with limited supply of oxygen, so pyrolysis. And then C would be charcoal is more energy dense fuel. And D would be burnt wood has more volatile organic compound, VOCs, than charcoal. So let's see, we'll give another 30 seconds, 40 seconds to get some answers. Yeah, I think we got the pool. Wonderful. Okay. So it sounds like 50% said it was A. We got a 59% saying it was B. And 45% said it was C. And then D was 55%. I guess you guys have all voted for different I guess option. It's all actually all of them. They're all applicable. So the wood as opposed to charcoal, it's just a way. It really is highly I guess impacted by the amount of oxygen. Charcoal will be a limited amount of oxygen as opposed to burnt wood. You know, it's uncontrolled environment, so you might have actually charcoal from forest fire because there was not enough oxygen and it burned at higher temperature. I think that charcoal is normally produced at like a close to 1,000 Celsius or in that neighborhood there. All right, thanks everyone for participating. There we go, my animation there. All right, so I did also contacted like I was saying, other labs to get some results, and the result it was anonymous, so like I couldn't provide more information than what is on the screen right now. But if we look at the top table in here, you see again KST, you see Pmax here, and then for the different particulate or different dust type, we have plywood in some cases. We got granular particle of wood created by sawing and machining, and so the values that we see green as opposed to burnt wood, again, we have a higher value for KST and Pmax. So I think the other slide was showing for the sample we had 108 for the highest, and in this case the wood hash was 125 and the 6.5, as opposed to greenwood, an average of 53 and 6.03 there. So interesting. Again, burnt wood seemed to be consistently like a little bit higher. And so how do we explain the higher value of burnt wood as opposed to greenwood? So if we look at a couple of different parameters, burnt wood, the likelihood of having a lesser amount of moisture, even though that in labs it is controlled. In a lab, they have to dry the sample to a lower value to, I think it's under 4 or 3 or 4, I can't remember the exact number, but the moisture has to be controlled. Where there's a big difference between green and burnt wood is the particulate size. So if you think about burnt wood, normally it is friable. So instead of like a saw, if you saw like a tree, you'd have like some flakes that are going to come out that are normally like almost ripped out, and it will cause fiber, larger particulate size, as opposed to when it's burned, it's more friable because there's quite a bit of carbon in there, and chemical composition. So burnt wood dust could represent a mixture of ash, tar, and carbon, and we've seen that there's also a potential for VOC leftovers in the wood here. So the bottom line is you need to understand what type of or dust you're dealing with burnt wood in your own process. So definitely recommend you to proceed with a dust test. You don't want to assume that it is an explosive or non-explosive. You got to do your test. You got to do some homework to characterize your dust. So now we've talked a lot about the explosibility, but how about the dust property? So wood dust toxicity, it can cause skin irritation, decrease of lung function, nasal cancer, dermatitis as well, which is, I didn't know, I had to look it up as well, that word. So it was skin condition of inflammation, irritation. As opposed to burnt wood, it's very similar burnt wood, but there's a pulmonary fibrosis, which is similar to silica dust and silicose. So like it scars your lung tissue, and it causes your lung capacity to be reduced. So the scar tissue will not allow your lung to breathe in where it's scarred. And carcinogenic risks as well for burnt wood. And you got to think about it. Finer particulates represent a higher risk for health. So anything that, if we look at micron size, so anything that's like 10 micron or below will have a more of a chance to get in the lungs and deeper in the lungs. So burnt wood is quite a bit more friable, so small particulate. So therefore, there's the risk of having that fine particulate being created that could be very dangerous for your lungs. Okay, so if we look at abrasive challenges, there's definitely more challenges when it comes to burnt wood, and there's different reasons for it. The particle size, so smaller particulate will actually have a higher wear factor, especially because the presence of carbon into the dust of the the bark and whatever it's been burnt there. There's not only dust, but there's also potentially fire retardant from forest firefighters fighting those fires. And the fire retardant agent can contain ammonia and different other chemical, I guess, composition that could actually harm also your equipment. So structural hardness for carbon, the higher the structure of the carbon, so carbon black, for instance, the more abrasive it is. So some of the equipment that will be affected by having that dust kind of attacking the equipment is obviously bearings. So bearing has grease, but whenever if the dust contaminates the grease, it will cause premature wear and possibly heat of the bearing and causing a failure on the bearing. There's blades. So blade as well are a challenge. When you're cutting something that's harder, you'll go through more blades. The dust collector bag as well. So finer particulates are hard to deal with when it comes to bag and cleaning. Electrical panel as well. So dust can get into electrical panel, cause all kinds of issues. And then there's corrosion by also the fire retardant agent that could lead into electric fault and then other corrosion issue around the equipment. So now let's talk about contaminant. So if you have a mill that's indoor and that there's a lot of different equipment transfer point and drop zone and all that, if you're not containing those drop zone or area, you will actually have a plume of dust that will be created and will actually generate a larger challenge. Instead of dealing locally where the dust cloud is generated, the dust will go all over in the mill and cause the dust to go on rafter, cable trays, and all kinds of different locations, causing also more challenge because dust is fuel. And so the more fuel you have in your environment, the higher the risk for explosion. So definitely recommend to follow the good principle of the industrial just ACGIH that I'm pointing out here. And providing a proper containment is essential to reduce the amount of airflow required by a dust collection system. And so I just want to point out to the bottom left here, this picture kind of show how velocity will reduce at a certain distance from where your hood is placed. So if let's say we have a ductwork here pulling from an enclosure here, the velocity right at the face here that I'm pointing out, let's say this is called 100%. So let's say 4,000 feet per minute, 4,500 feet per minute. So at one distance away, one diameter. So let's say if you've got a foot here, 1 foot away from the face here, your velocity will drop at 10%. So you'll be at 400 feet per minute. It's reduced quite a bit, really, really fast. So at some point, if you're too far, if your hood is not located at the right position or it's too far, it will have a very small efficiency to remove the dust that you're trying to capture. That's why it's so important to have proper containment around where the dust is actually mixed or pushed into the air, as an airborne dust. You don't want that to happen. And therefore, different example here, this is the bark to the bottom right here that's been enclosed, and there's definitely a challenge of enclosing certain equipment because of access to maintain the equipment or visual of productions and all that, but it's definitely possible. You just have to put a little more effort into it. So there's another option also available in some cases, not all the time, but you can use water as an abatement method to deal with dust, especially when it's airborne. So the pros of using water is you're elevating the moisture, and by having a higher moisture, you're reducing the risk of an explosion, because we know that dust at 25% moisture or higher typically is considered non-explosive. It's a good method also to deal with large areas. So if your dust is already airborne, you can use mist and then kind of try to trap that mist with the dust and then knock it off the airstream. There's cons, obviously. So dealing with contaminated water in the industry is a challenge when you use water for that reason. And then also you're adding potentially some corrosion because of using water, especially in the building. But there's it has its place, outdoor, let's say for biomass, like this is a huge pile of material without the using the water as a misting agent to knock the material. You see the left side here, how dusty it is, and on the right side it's quite dry, and there's not much dust being generated here. Mark, I see you again on the screen.
Yeah, for sure. I guess I'm wondering how can a mill even prepare to process this burnt wood, other than a couple things you mentioned?
Yeah, there's definitely different ways to approach it. And I do have a slide coming up in a couple slides, but I can summarize it briefly. It will be a bit more of a challenge for sure, but it starts with understanding your dust. So having a dust test done, understand how explosive it is your first step. And then second thing I would say is to update your dust hazard assessment, your DHA, and understanding where the hazards are. I'm just talking explosion, explosion risk. And the third one is just also reviewing your process and how it's done. Maybe your dust collection system doesn't have enough extraction capability to handle that finer particulate. And you might have to look at upgrading your dust collection system to do a better job, or containment. It's a combination of different things that you may have to look into.
Awesome. Thank you.
So moving on to a case study here. I want to be conscious of the time. I think we have about 24 minutes left, so this shouldn't take too long. So this case study is interesting. So it's a biochar process. So it's turning wood byproducts like wood chips, or to the bottom left, we kind of see the material here, into biochar. And the reason for it is to enhance the soil property. So there's having biochar actually is a super soil. It's called a super structure, and it helps retaining more water, and it actually locks also some of the nutrient more and release it slowly in the soil, instead of having, let's say, certain fertilizer and then you put it in the next year it's all gone. That biochar will lock in the fertilizer, and then will release it slowly, so that you have a constant, your soil is not like completely stripped of its nutrient every year. And also it's a way for them to lock carbon, for carbon conscious in the environment there, to lock it in for many centuries using the biochar. So it is called a pyrolysis process. So pyrolysis again is it's a control environment for the oxygen, so limiting the oxygen there. So we talked about different challenges. On this one specifically, we noticed that the dust filters were very difficult to clean. So the finer particulate were really sticking on the fiber, and finer particulate, think about it with in perspective of the fiber itself. So if you zoom into a filter, when it's clean and it hasn't been installed, the fibers have a certain space between each other, and so finer particulate can actually go deeper in the fiber because of those holes existing than actually larger particulate that would just stick to the surface of the filter. So by going further in, it will be harder also to remove the dust and pulse it outwards and clean the filter. So the main I guess challenge that we've seen on this one was that the filter actually had an increase of pressure across the filter. So the fan and the air moving, in order to go across the filter, there's a static pressure that is happening. So the fan has to overcome how difficult it is to go through the filters. So the dirtier the filter, the higher the pressure across the filters, and you're burning additional also horsepower from your fan. So if let's say it was a simple dust to deal with, the pressure across could be like a 1 or a 2, and then it could stay there for a very long time. But because of that dust being finer and then more cleaning on the filter, It went all the way to like a 4 or 5, and it stayed there, and it was impossible to put it back into like a 1 and a 2 inches of water for the cleaning system there. So you're burning more horsepower at the end because of that. And also we found there were some challenges around dust going into the different electrical cabinets, causing also like dust buildup. And then if you, let's say if you have a VFD where we have a fan to cool the VFD in the cabinet, and there's a filter here, let's say, well, the filter can get clogged and then you don't have the proper cooling effect inside the cabinet, leading to potentially a failure of overheat in your cabinet, or having dust just getting into the cabinet and causing like potentially like who knows, a short or short circuit, or a premature failure. So it's important when you deal with burnt wood dust to select your electrical cabinets and the electrical to a proper rating. So here on the top there we see a table that shows the NEMA table. So it's basically a rating on different contaminant in the environment. So there's, dust, oils, all kinds of different things. What we recommend for burnt wood is to at least a NEMA 12 or a NEMA 4 or NEMA 4X. 12 is kind of the bare minimum, 4 is a higher rating, and 4X would be kind of considered more of an explosive environment there. And there's also the electrical classification. I won't spend too much time into it, but we've seen KSTP max, MIM, MEC, and all that. So if the dust is very explosive and has a low minimum ignition energy or explosion concentration, it could change your electrical classification to a more stringent, more, higher risk for an explosion there. So keep that in mind. All right, another issue that we did have also on that side was a high wear. This is a rubber tip airlock valve that's certified also for explosion as an isolator. And we've seen a lot of premature wear on the rubber airlock to the point where it affected how it operated, and it didn't seal properly. So there's more maintenance requirement. So like to replace wiper because of the wear on the carbon, especially around the burnt wood dust. See different gaps here that generate. So when those gaps are happening, what it does is causing the material not to be removed from the dust collection system or whatever it's connected to, because there's no more an airlock. The airflow can actually go through if there's suction, or the pressure is different on that side as opposed to the other side. Air can actually pass through those little cracks. And so you can actually have issues offloading the material from your collector. Another issue that we've noticed on that side was the challenge around air quality, for outdoor air quality, to make up some of the air that were removed from the plant. So typically when you have a dust collection system, you have two options. We can either recirc the air back in the building if it's legally allowed. So any carcinogenic, you're not supposed to recirc back in the building. So if your dust is carcinogenic, that's a no. And if you don't recirc back in the building, you need to make up the air. So if, let's say you're pulling a 30,000 CFM out the building, you need to replenish the air. Some of the plants we've seen is the equipment here is not existent. And what happened is, if you don't have a replenished, air will find its way back in the building, but you won't like it. Anytime you have a door opening, it's going to be really hard to pull it. You'll be negative. So it'll be hard to pull it, and the door will actually try to slam back in. In this instance, we had a makeup air unit that was installed, but the challenge was to find that proper quality. And the original install was as you're seeing here, but we end up actually extending some ductwork to go above the roof to really pull some clean air in order to bring that fresh air that has no contaminant or dust generated from the surrounding there. So this is almost the end. This is my last slide here, awareness and solution. So we've seen that the burnt wood dust has some challenges. And the challenges are especially around the explosibility of the dust. I highly recommend, if you're dealing with some explosive or burnt wood process right now, to retest your dust. And unfortunately, in the industry, I think this is something that's lacking a little bit. There is no extensive white paper or documentation on burnt wood that I was able to find and as guideline. Where I would love to see that going is having some type of a lab taking that on their upon themselves to actually push that through and establish a certain standard of like best practice. So for the challenge is to find where you can harvest a tree that's burnt and then test it and it can be non-explosive, and then a month later you can do the same test and it will be explosive. So understanding the ranges and where that dust explosibility can be in the industry by collecting a large amount of sample and then having something done that can give guidelines, say, okay, well, that value is, let's say, 150 KST and below, or 150 KST, you're covered for most of the application. That'd be pretty sweet to have that, but we don't right now. Update dust hazard assessment, so that your dust hazard assessment is important when you deal with new type of dust. You got to update that, or every 5 years. So that needs to be reviewed. And then review your explosion protection system. We talked about explosion vent. We explained that earlier in some of the slide, but how about your blast zone? So when there's an explosion, there's a certain throw of flame going out from the panel into the area where you're venting. And so if the KST is higher, what will happen is, that distance will be further out. So sometimes you might be okay with the green wood and the blast zone, but what about the burnt wood? If the values are higher, then you might have a false sense of protection there. So reevaluate that is important. Also looking at your spark detection system to mitigate the risk. If the dust is drier, it might be a good idea in processes where there's a high risk of spark. And if you don't have a spark detection system, to add one in, and alongside with either a spark and abort gate system or a spark and spray system. Also, your capacity for dust collection system or your containment might be insufficient. So recommend to have a bit of a study done on that to make sure that your system is in good shape to handle that. Some of the thoughts that goes with this is like, maybe your filter in your baghouse is not necessarily ideal for the burnt dust, and you might have some issues with filters plugging too quick. And so selecting a filter that has a bit more of a better behavior with that dust could be a solution to that. And then the last one would be also investigation of the air quality level inside the building, so that you're not exposing your staff on higher level that are above the regulations there. And that could lead into long-term issue when it comes to breathing that dust. And so this we're about 10 minutes, 12 minutes away from the end of the webinar. So thanks for everybody for your attention there. And I'm Mark and I will be taking some questions right now.
And you bet there are questions.
Right on.
So first one, are existing explosion vents typically designed to accommodate the values that we're seeing with burnt wood? Or is the safety factor sufficient?
It's a great question. It really depends on how it was designed. So it's site specific, and that's the kind of the challenge. Like, I don't want to do a blanket statement that you're good or you're not good. Some cases, depending who's designing it, and should be designed by someone that's knowledgeable, a professional engineer in Canada. But depending who designed it and how challenging it was, sometimes the engineer was maybe didn't have enough room for more than certain amount of panels, and so that KST being higher could just push it above what you currently have. It might not be the case, but it's important to review those documents and making sure that you're okay. Where the biggest challenge I would say for venting is around cyclone separator. Cyclonic separators are challenging to vent as it is, and often you're really close to the limit of your KST. So having a higher KST can actually really be a nightmare when it comes to venting a cyclone.
Excellent. So we have a question about the dust properties chart. Is there a range of burnt wood within the debarker? And I think to clarify this, it's how burnt is the bark by percentage?
Yes, this is a great question. I can circle back with whoever asked that question because I don't have the answer. I think it's specific to each forest fire, unfortunately. Like it's a non-controlled burn normally for a forest fire in the sense that the oxygen level is never controlled. So it's subject to the element. If it's really windy when it was burning or it was a calm day, you might have a different result. And species also, like there's a lot of factor that will affect how the bark is burnt and how much.
And one thing I can offer is I'm pretty sure that when a mill is running burnt wood, they're running all burnt wood until they're done the batch, and then they go back to whatever.
Yes.
Another interesting question. So, do we have any information like such as an MEC for wood ash?
That's a good question. I don't have that with me, but wood ash or fly ash, I was reading about it, and there's definitely some challenge around that. So there's if you look at the event and explosion, there was some explosion with fly ash in the past. So you might think, hey, fly ash is coming from, let's say, coal that's been burned, so there's no way it's going to explode, but there is still a risk. And there was an explosion. I think it was in Nova Scotia of a silo that exploded with fly ash.
Okay. So with the increasing fouling in the filters from this kind of dust, I think we're talking about the biochar. Is there a suggested increase in maintenance? Is there tar in the dust? Would pressurized air release this, or would we need some kind of soap to clean off the particle?
Yeah, so it all depends on certain parameters of the bag house. So there's certain terms that I can expand on a little bit, but how fast the air moves through the filter is a very important one. So if you're going very fast, what happens is almost like you're getting the dust embedded in the fiber, as opposed to if you're going very slow. Think about it in the sense of this way I can explain it is like, if you're dealing with steel beads going in the bag house versus feathers. Feathers will be like staying in the airflow for quite some time, and it'd be very hard for that feathers to fall off the airstream. So you have to slow down the air quite a bit when it gets into the enclosure of the bag house, as opposed to the steel bead. You can go quite fast and it's still going to drop. And so this is the idea is the air to clot ratio, so number of CFM per square feet on your bag house. So if you don't have that proper ratio for burnt wood, you might actually end up operating at higher static and causing, more energy to be used to operate, as opposed that if you have like more bags, it would slow down everything and it would run smoother, and you would have that high static across the bag. That's one of the many different I guess there's different other parameters. The other one is the can velocity, like so the air moving upward into the bag before it gets into the bag. If that's too fast, you might have some issues. And if the bag house design, there's not enough space between each bag, that's called the interstitial velocity. That could cause also issues with burnt wood and that dust not being able to be removed from the bag. Along with the health of your self-cleaning system. If your self-cleaning system is not optimal, it might not be able to knock that dust off the filter.
Cool. Thank you. I have a question about how the explosive quality of biochar might compare with the burnt wood.
Yes, so biochar that result, I'm just going out of memory for the case study. There's something I was not sharing, but I think we were in the neighborhood of 150-ish. Remembering that, a pyrolysis um, is controlled oxygen level, so that it's more fuel dense for charcoal, and so that explained possibly the result, because there's more reaction with oxygen still in that final product.
And I would say, to add to this, the biochar is like a controlled process where they have a more of a known product, and the burnt wood is uncontrolled, and we won't know exactly how it will come out.
Correct. That's right. Good point.
Another question here about explosivity testing. Is there any fundamental different method for the coke or coal than with other dusts? I guess, would there be any different kind of preparation for the explosivity testing, or would they be different than typical cellulose material?
It's a good question. So the cold testing is very specific to the coal. I spoke to different labs, and they said that specific test would be the most representative for burnt wood dust, if you're sending to get characterized. So they felt that there was enough parameters to, even if it's not coal, burnt wood, that it would be representative of the VOC that you want to understand there.
Okay. So we were talking about the moisture control, or using moisture to control dust ignition. Does moisture have a potential to cause auto ignition for the burnt dust?
Auto ignition, I didn't see anything in the documentation that would lead to say that it was a for sure thing. It really depends on, I think, the species and the VOCs, but I was not able to have some documentation that states yes, that hardwood was there was a risk for auto ignition. I was not able to find any documentation to support that theory. Not to say
Okay.
that it's not possible, but I'm just saying I haven't come across that.
Um, I feel like this is a good question, maybe not quite about the burnt wood, but is there a way that these tests can also be used when we're dealing with more of an agricultural product, like maybe flax or straw?
So I'm referring to the VOC characterization, or to the ASTM
Let's talk
1226.
about KST, MEC, etc.
Absolutely, yes. It's the same test, KST, PMAX, and all that for anything that's organic. So we use the ASTM 1226 for let's say grain industry, or the wood industry. Obviously, the preparation, the lab have their little recipe when it comes to drying the material and all that, but it's processed in the same chamber.
Excellent. And I got one last question, and I believe we can say that we've done well. We have someone is wondering if there is a risk of wood being processed where they might not be completely extinguished from that forest fire.
I've heard that smolders sometimes, especially like when it's on the ground, can last for a very, very long time. Um, if it's yeah, it's like a forest fire, like, or something like that, it can stay kind of dormant for a very long time. I haven't seen, though, in the history of explosion and fire and all that, any correlation to um point that the fire was still active when it got to the mill. So I can't say it's impossible, but I cannot say, well, it's gonna happen for sure. So there's not enough actually documentation, I guess, in the industry yet to be affirmative on that.
All right. Well, thank you. Thanks you everyone for the questions. I'm going to turn the time back over to Alex to bring us home here.
That was awesome. Thank you guys so much for that presentation. Really appreciate it. Like Mark said, unfortunately, that is all the time that we have for the webinar today. I just wanted to once again extend a thank you to VETS for sponsoring this webinar today. Also, just wanted to thank our presenters, Mark and Francis, once again for being here today to give this awesome presentation. Finally, just want to extend a big thank you to the audience for your questions and participation. Watch your inboxes for a link to the recording and any answers to questions from today's session. Thanks, everybody. I hope you have a great and safe day.
Thanks, everyone.